Today we will be talking about Lewis diagrams. A valence electron is an electron located in the outermost shell or valence shell of the atom that can be transferred or shared with another atom. When it comes to the valence electrons in the main group elements, there are some definite patterns. Atoms that are in the same column have the same number of valence electrons. This table shows the number of valence electrons that are characteristic for each group. For example, the alkali metals have 1 valence electron, the halogens have 7, the noble gases have 8, and so forth. It's a little messier when you get to the transition metals. Here the trends are not so clear. Now, if we're talking about the outer shell, most transition metals have 2 valence electrons, since their outermost energy level tends to have an electron configuration of whatever the row is, S2. Now, the exceptions are cobalt and copper, which have an S1 configuration in the outer shell. However, transition metals also have electrons in d orbitals, which are very close in energy to the s orbitals in their highest shell. When it comes to forming ions, they often are able to recruit electrons from their d orbitals, hence they can end up with a number of different charges depending on how many electrons they give up. This is why we have to use Roman numerals when we name ionic compounds that have transition metal cations. The lanthanides and actinides have similar issues. But today we're going to focus on covalent compounds, which occur between nonmetals. So let's move over to the right side of the periodic table. We can bring hydrogen with us, since it also participates in covalent bonding. Covalent bonds form when atoms share electrons. Lewis structures are one tool or model we can use to better understand covalent bonding. This model is attributed to G.N. Lewis, who was an American scientist in the early 1900s. In Lewis structures, the valence electrons are represented by dots that are drawn around the symbol for the atom. This table shows some Lewis dot structures. You can see that only the valence electrons are represented. Here's an example. Fluorine has 7 valence electrons, and they are represented by 7 dots. Most atoms are happiest when they have 8 electrons around them, or a full octet. We call this the octet rule. They tend to form covalent bonds in such a way that they can share enough electrons to make a full octet happen. They want to achieve a noble gas configuration because this is energetically favorable and it makes them stable. An exception is hydrogen, which only has 1 electron. It wants to form a full duet. That means 2 electrons. Now back to our Lewis dot structure for fluorine. Fluorine isn't very stable as a single atom, and it wants to form a full octet. One way it can do this is to bond covalently with another fluorine atom. We call the electrons that participate in forming bonds bonding electrons. The electrons that do not participate in bonding are called lone pairs. A single shared pair of electrons is called a single bond. A single bond can be represented in 2 ways in a Lewis diagram. It can be represented with dots or with a line. Either way is fine as long as you remember that a line represents 2 electrons. 2 pairs of shared electrons form a double bond. Once again, we can represent the double bond using 4 dots or using 2 lines. Either way is correct. 3 pairs of shared electrons is a triple bond. We can represent it with 6 dots or with 3 lines. Lewis structures can also be drawn for ions, but ions are typically shown in brackets with the charge on the outside in the upper right. So, let's talk about how to make Lewis diagrams. There's a set of rules we need to follow. We're going to use water as an example. The first thing we're going to do is to find the total number of valence electrons for the atoms in our molecule, or ion. And for water, we get 1 valence electron for the first hydrogen, and 1 valence electron for the second hydrogen, and 6 valence electrons from the oxygen. And this gives us a total of 8 valence electrons. The next thing we need to do is to figure out which of the atoms is the central atom. This is usually going to be the least electronegative atom, except when there is a hydrogen or a halogen like fluorine or chlorine or bromine. Hydrogens and halogens tend to be terminal atoms. That means they're on the ends of the molecule. So for water, our oxygen is going to go in the center and hydrogen will go on the ends because it's always a terminal atom. In step 3, we're going to connect each atom to the central atom using a single bond. Then we're going to subtract the electrons that we used from our total number of electrons. So in our water example, we have used up 4 electrons and we have 4 remaining. Now we could also have used a line to show our single bond. Next, we're going to distribute the remaining electrons as lone pairs on the terminal atoms, except for hydrogen. Then we're going to subtract the number from our current total of electrons. In this example, hydrogen doesn't get any lone pair electrons because it's happy with a full duet, so we're going to skip this part. Next, we're going to place all remaining electrons on the central atom. If the central atom has an octet or exceeds an octet, we're usually done. But if the central atom doesn't have an octet, we need to rearrange the electrons to make double or triple bonds. Double bonds generally only form between carbon, nitrogen, oxygen, and sulfur. Triple bonds generally only form between carbon, nitrogen, and oxygen. Now, water was a very simple example because there were a lot of steps we didn't need to do because of those terminal hydrogens. But now we're going to do a slightly more complicated example and draw a Lewis diagram for hydrogen cyanide. The first thing we'll do is find the total number of valence electrons in the molecule. We'll add an electron for every negative charge if it's an anion, or subtract an electron for every positive charge if it's a cation. This is a neutral atom, so we don't need to do this. For hydrogen cyanide, we have 1 electron from hydrogen, 4 electrons from carbon, and 5 from nitrogen, and this gives us a total of 10 electrons. The second thing we're going to do is decide which atom is the central atom. The least electronegative element is going to go in the center. We also need to remember that hydrogen and fluorine and other halogens are always terminal or end atoms. So in our example, carbon is the least electronegative, and we're going to put this in the center. In step 3, we're going to connect each atom to the central atom with a single bond. Then we're going to subtract the electrons from the total in step 1. So here we're going to subtract the 4 electrons we used up, and we now have 6 remaining electrons. The next thing we're going to do is distribute the remaining electrons as lone pairs on the terminal atoms, but not on hydrogen. And then we'll subtract the electrons from the total in step 2. Now, we used up all 6 electrons, so we don't have any electrons remaining. Now, if we had remaining electrons, we would put them on the central atom. And we would be done if the central atom had an octet or had more than an octet. But here our carbon has less than an octet, so we're going to have to create multiple bonds. We do this by sharing 4 of nitrogen's lone pair electrons with carbon. Nitrogen and carbon are now sharing 6 electrons total, and this is a triple bond. Now we can see that carbon has a full octet. It has 4 valence electrons of its own, and it's sharing 1 more electron with hydrogen and 3 with nitrogen. Now we can draw our Lewis structure with dots like this, or we could also use lines like this. What if you have an ion like formate, CHO2-? Well, the process is fairly similar with a little twist. The first thing we're going to do is find the total number of valence electrons in the ion, and then we're going to add an electron because it's an ion. So for this particular molecule, we have 4 electrons from carbon, 1 from hydrogen, and 12 from the 2 oxygen. We're going to add a 1 for the extra charge, the -1 charge. This gives us a total of 18. Next, we're going to decide which atom is the central atom, and this will be the least electronegative element. That'll go in the center, and that will be carbon. Hydrogen's going to be a terminal atom, and the oxygens, because they're more electronegative, will also be on the ends. The next thing we're going to do is connect each atom to the central atom with a single bond. We could do this with dots or lines. We'll do it with dots here. And then we're going to subtract the electrons we used up from the total. We used 6. 18 minus 6 is 12 remaining. Next, we will distribute the remaining electrons as lone pairs on the terminal atoms, except for hydrogen, and we'll subtract these from the total in step 2. So we will put all of these electrons around the oxygens, and we have 0 remaining. Now, if we take a look at this, we notice that carbon only has 6 electrons around it. It does not have a complete octet. So we're not done. We're going to need to create multiple bonds. We're going to do this by taking 2 of the electrons from one of the oxygen atoms and moving them over so that we form a double bond between oxygen and carbon. So now carbon has a full octet. Could we have made the double bond with the other oxygen? Sure, we could have made it between either oxygen, and we'll get into this in a future lesson. Well, we're going to take this ion, we're going to put it in brackets, and we're going to put the negative charge up in the right. There are a few exceptions to the octet rule you should know about, and these will be important when we look at molecular shapes. Boron has 3 valence electrons. Sometimes it forms an octet, but sometimes it doesn't. It usually does not form double bonds. Aluminum follows similar trends, and beryllium is also perfectly happy to not have an octet. Atoms in the 3rd period or higher are able to recruit some of the electrons in their d orbitals to share. Examples of these are phosphorus, sulfur, iodine, xenon, and a few others. We call this an expanded octet. So it's not unusual to see a configuration like this where the central atom has more than 8 electrons and is directly bonded to 5 or 6 other atoms. Some molecules that contain an odd number of electrons form structures with less than an octet. One example is nitrogen dioxide, which has this Lewis structure. Molecules that have unpaired valence electrons are called radicals, and these are typically highly chemically reactive. So let's review. Lewis diagrams can be constructed according to an established set of principles, and these structures are especially important in helping us to better understand covalent bonding. You should now be able to represent a molecule with a Lewis diagram.